We are on to simplifying roots. So we're deep in this root unit. You guys ready? Okay. All right, we got to simplify some square roots. So we're just going to remind ourselves about all the perfect squares. Well, not all of them, but a bunch of them. So let's list out, take a minute, list out the first 10 perfect squares. Emmett, give me a bunch of your first perfect squares here. What do you got?
1, 4, 16, 45. Oh, yeah, 9.
That's okay.
25, 36, 49.
121, okay, good, good, good. Obviously, we can go here all day, but the first bunch usually satisfies most of the problem here. Okay, so when we simplify a radical, all right, specifically a square root, you need to break it down so that you have a perfect square times a non-perfect square. Okay, so somebody has to be a perfect square. Somebody from that list times somebody else. Okay, unless you just know the answer off the top of your head, like it already is a perfect square, you need to break it down. So for example, should you know the square root of 16, or do you have to break that down? You should know it. That is just the number 4. Okay. Bless you. However, the square root of 50 is not something you should know. You have to break that down. So your goal is to say, I need a perfect square and a non-perfect square. So I need somebody from my list times somebody else. So who makes 50? Good, 25 and 2. And again, I needed a perfect square, and then somebody that's not a perfect square. Okay, so now you say, which one do I know? Square root of 25 is the number 5. Do you know the square root of 2? Then it stays in the root. So the one you know comes out, otherwise it stays in the root. So this simplifies to 5 root 2. I'm going to skip to the one right below, root 18. Is that a root you should know? No, all right, so break it down. We need a perfect square and a non-perfect square. 9 and 2, beautiful. So we're going to go square root 9 times square root 2. Which one do we know? 9, so you can kill it, and it becomes a 3, and then I leave square root 2. Okay. Okay, let's try, we talked about this earlier this week, the square root of negative 16. And that means there's two numbers, the same two numbers, that can multiply to a negative 16. Is that possible? No, because positive 4 times positive 4 is positive 16, and negative 4 times negative 4 is positive 16. So this does not exist yet again this week. All right, so this course hits mostly square roots and cube roots, and then it'll throw some higher roots in every now and then. So let's talk about some cube roots. Let's maybe just off to the side list some perfect cubes. Okay, obviously 1 is a perfect cube. What's the next perfect cube? 8, good. Next one? 27, 64, maybe one more? 125, good. Now, obviously you can sit there and keep getting more if you need them, but usually it's one of the first couple when we get to perfect cubes. All right, so perfect cubes work the same way. You would need a perfect cube times a non-perfect cube. Thanks, Leo. Perfect cube times a non-perfect cube. Okay, so if I look at the cubed root of 8, do I know it or do I have to break it down? You should know it. It's in your list. The perfect cube of 8 is just the number 2. Okay, how about 16? Is it a perfect cube itself? Clearly no. So I need a perfect cube in somebody else. Who can I use? 8 and 2. Now make sure you keep the cubed root. So it's the cubed root of 8 times the cubed root of 2. Okay, so now you say, which one am I supposed to know? The cubed root of 8 becomes the number 2. So it's 2 cubed root 2. Make sure you keep the cubed root. All right, now again, earlier in the week we did talk about negatives. Can I find a number 3 times that multiplies to a negative 8? Yes. What number is that? Negative 2, right? Negative 2 times negative 2 is a positive, and then times another negative is possible. I can get a negative 8. So the cubed root of negative 8 is negative 2. We said odd roots you can take negatives of, but you can't of even roots. All right, let's go cubed root of negative 54. Is that in our perfect cubes? So I got to break it down. Who goes in there? 27. Good. So cubed root. Now I want the negative to stay with the perfect cube. Negative 27 times the cubed root of 2. Okay. What is the cubed root of negative 27? Really close. Negative 3. And then I'm going to keep cubed root of 2. So minus the cube roots, all that root stuff you broke down in Algebra 1 and geometry when you simplified things. Now in Algebra 2, we start throwing variables all under the roots. Okay, so that's the next part we're going to attack here. So I'm going to do it the long way. My goal is that you might be able to find a shortcut. So if you find the shortcut, you are free to use it at all times. I'm just not going to tell it to you. You got to find it on your own. So here is the long way on how to do this. There's a negative out front that's going to stay. This is a what type of root? Square root. So in theory, I have to have all perfect squares in here, right? So I can say it's the square root of a squared times the square root of a squared times the square root of a squared. Because when I multiply, I add exponents. That's 2, 4, 6. So a to the 6, I'm breaking up into perfect squares because this is a square root. Now what happens to my square and my square root? They cancel, and that just becomes a. The square and the square root cancel, and that becomes a. The square and the square root cancel, that becomes a. And I am left with a times a times a, or negative a to the third. Okay, so I'm going to do another one the long way, and then see if you can figure this out maybe a little quicker. Again, this is a square root, so I'm breaking them into perfect squares. Okay, example 2, I have a square root again, so I'm going to break everybody into perfect squares. So I'm going to have x squared times x squared. That's 2, 4. Y to the 5th, I'm going to have a y squared. Oh, y squared, that's 4, but I need 5, so I have to have one more y. Then z to the 6th, I'm going to have z squared, and z squared. This square and square root are going to cancel, so that just becomes an x. That becomes an x. That becomes a y. A y. Now, does this one cancel with anything? No, so that's got to stay in the root. Then this z squared cancels with that. That cancels. That cancels. And let's see what we're left with. X times x is x squared. Y times y is y squared. Z times z times z is z cubed. And then I have one root y left over. Does anyone think they see a quick method, perhaps? One person, 2, 3, 4. Okay, take a minute, talk to your partner, see if you can come up with a method. Well, I meant by talking to your partner.
Yeah, I did.
Oh, okay. What are we noticing? You kind of cut it in half, all right? So that's a good... Now, let's think about why it got cut in half. What is the name of this root? Square root. And think about the rule we've been talking about all week. We can rewrite this as a to the what power? 6 over 2, because roots go on the bottom, and 6 over 2 should just become a 3. Does that make sense? Try this one. I have x to the, well, square root of x to the 4th, so I can rewrite that as x to the what power? 4 over 2. Then this should be y to the 5 over 2, and z to the 6 over 2. So in theory, 4 divided by 2 is 2. I should get x squared, which I did. I'm going to skip the y's for a second. 6 divided by 2 is 3, which I got, z cubed. Okay, now let's talk about this one. 5 halves. How many times does 2 go into 5 nicely? Twice, so I pulled out a y squared, and how many oddballs are left over? 1, so 1 has to stay in the root. There's 1 that did not come out. See if you can do this one without writing it out. I'm going to write them as the fractional exponents. Who should I get? X to the who over who? 3 over 3. And then y to the 12 over 3. So I should be left with just xy to the 4th. Okay? So the long way is to write out all the perfect pairs and then cancel them all. But hopefully you can go back from the rational exponent to the radical. Go ahead and try 4 as well. What are you two, starting a band back there? B to the what power? 4th, and C to the 1st. Does that work for everyone? Have I lost anyone? No, you don't have to write the 1. No. All right. I'm going to skip 5 for a second and jump to 6 just because it's a square root versus a 5th root. All right. So I'm going to break this up as the square root of 25, and then I have the square root of all these guys. X to the 10th, y to the 4th, z squared. Do I know the square root of 25, or do I have to break it down? We should know it. That answer is just 5. Okay, and then let's write these as the fractional exponents. X to the what power? I'm going to go fractions first. 10 halves, but you're right. 10 halves, y to the 4 halves, and z to the 2 halves. So this looks like it's going to come out nice. That's going to be 5x to the 5th, y squared, and then just z. All right, let's go back and look at 5. So now we have a 5th root. Okay, so it's odd, so the negative's okay because it's odd. So I'm going to kind of break it down. I need the 5th root of negative 32 if possible. And then I'll have x to the what power? 15 over 5. I'm going to write it out slowly first, but you're right. 15 over 5, and then y to the 20 over 5. All right, so we'll take care of the easy part. Yes, that became x to the 3rd, y to the 4th. Do we know the 5th root of 32? We should know it. We should know the 5th root of 32. It's 2. 2 times 2 is 4, 8, 16, 32. Now, because it's negative, we can keep the negative, so it's a negative 2. So as those roots get bigger, you might have to write out some of your perfect whatevers. Is there like a full moon or something going on here? All right. Go ahead and get 7 and 8. 7 and 8. All right, so how are we writing this exponent? X to the what power? No. 3 over 2. Y to the 6 over 2. And z to the 9 over 2. Again, that's what we've been kind of practicing for 3 days, going from the radical to the fraction. All right, which of these would you consider nice? The y. The y is going to become y cubed. Okay. So now we have to say how many ones go in nicely. How many of these are going to go in nice? So 1 comes out. And how many are left? 1, right? 2 goes into 3 once with a remainder of 1. So there's still 1 over 2 left. It's got to stay with the root. How many times does 2 go into 9? 4 times. So z to the 4th is coming out. And how many are left? 1 out of 2, because we have to keep that denominator. So my final answer, I'm going to take all the nice ones, this, and this. So I have y cubed, I have x and z to the 4th. Now these still are technically to the 1/2, so they are back inside the root, x and z. Okay, they still have the 1/2 power. They did not come out of the root. They only came out if they went in perfectly. Anybody else is left inside. All right, let's look at 20. Do we know the square root of 20, or do we have to break it down? Okay, so we need a perfect square and a non-perfect square. Who can we use? Perfect. 4 and 5. And then rewrite each of these as fractions. X to the 1/2, y to the 7/2, and z to the 12/2. Have we lost anybody there? Alex? So we're just showing how many times it goes in and then how many are left over. The 4 becomes a 2. Don't know the square root of 5, so it stays. Can 2 go into 1? So it stays. Okay, so that is still x to the 1/2 or the square root of x. Can 2 go into 7? 3 times. So 3 groups come out. How many are left? 1. The remainder is 1. 3 times 2 is 6. The remainder is 1 out of 2. 6 goes into 12. Oh, that's supposed to be a 2. My bad. That's my fault. 12 goes into 2 6 times. I think I was doing the math in my head at the same time. All right, so the nice pieces are 2. Whose else is nice? Y to the 3rd, C to the 6th. Now everybody else has the half, right? So they all go in the root together. The 5, the x, and the y. Okay, so that's why we're leaving the half to show that they go back inside the square root. The root is 2. Roots are on the bottom. Let's skip down into 11 just because it's a square root versus the other roots. 200 is not on our perfect square list, so break it up and rewrite each of these. Yes. At the end, you want to put them all back in the same root. Stop. Who are we using for 200? Good. X to the what power? 55 over 2, 120 over 2, and 3 over 2. The root 100 just turns into a 10. Okay, how many x's are going to go in nicely? 27. So 2 times 27 is going to get me 54. How many is left then? 1 out of the 2. 120 over 2 is going to get me y to the 60th. Goes in beautifully. All right, 3 halves. How many go in nice? 1. How many are left over? 1 out of 2. And then again, all the nice ones come out front. So the 10 comes out front, x to the 27, y to the 60, and z. Everybody else goes into the root. So I've got a 2, an x, and a z. And they all just go back into the same root. All right, let's go to the cubed root. Let's go up to number 9, cubed root. Is 16 a perfect cube? No, so you got to break it down to somebody on your cube list and somebody not. So 8 and 2, and I need the cube to stay negative because we can take the cube of a negative, so negative 8 and 2. X to the what power? 5/3, good, and y to the 10/3. Okay, so the cubed root of negative 8 is the one we know. That turns into a, really close, negative 2. Okay, I don't know the cubed root of 2. Okay, how many nice x's can I take out? 1. Now be careful. How many are left? 2/3. How many nice y's can come out? 3. And how many are left? 1/3. Okay, if they don't go in nicely, it's the remainder over what we were dividing by. Keep that in there. So now when we pull out the nice terms, I'm going to start with a negative 2. What else is nice? An x and a y to the 3rd. Now notice this is really cubed root, cubed root, cubed root. So they are all going back into the cubed root. That's a 2. This is really an x what? Squared, good, and a y to the 1st. That's going back in there. Okay, powers on top, roots on the bottom. All right, one last one. Every now and then they'll throw a 4th or 5th root at you. So we don't have the 4th roots written out. I don't think that is a 4th root. So let's start low. 2 times 2 is 4, times 2 is 8, times 2 is 16. So 1 is a perfect 4, 16. 3 times 3 is 9, times 3 is 27, times 3 is 81. I think that's already too big. So it's got to be 16 and 3. 16 and 3. So careful how you write your exponents now. So I'm going to have x to the 6/4, y to the 12/4, and z to the 17/4. I'll give you a minute to rewrite it. Fourth root of 16 becomes a 2. I'm going to keep the 4th root of 3. How many x's are we going to take out? 1. How many are remaining? 2 out of 4. Don't reduce that, just leave it as 2 out of 4. How many y's come out? 3. How many z's? 4, with how many left? 1/4. Okay, so the reason I said don't reduce this is because everybody's going back into the what root? 4th root. So I don't want to have a half here. Just leave it as a 4. So I'm going to have the 2, the x, the y cubed, and the z to the 4th. Those are all the nice ones. And then inside the 4th root, I'll have a 3, x squared, and a z. Right, all inside the 4th root. So the number inside here has to be smaller than the index outside as we're going through. All right, flip to the next page. Let's try some, well, try a couple nice ones and we'll try some ugly ones. Try to do like 1 through 23. I think those are all super nice.